All right, gentlemen, today we're going to talk about solving systems with 3 variables. You guys already know how to solve systems with 2 variables by graphing, by substitution, and by elimination. Today we're going to take it a step further and solve when we have 3 unknowns. So why do we need to know this? Well, now we're going to be able to solve, again, problems where there's 3 different variables. If I told you that the Philadelphia 76ers scored 117 points in last night's game, and they made a total of, let's say, 59 shots, you would be able to tell me exactly how many free throws, how many 2-pointers, and how many 3-pointers they made in that game. Before we get into solving systems with 3 variables, it's important to know what we're talking about. So since there's an X, Y, and Z, we are now talking about 3-dimensional planes. Since there's a 3rd variable, it adds a z-axis into the problem, which makes graphing very difficult. If you look down in the bottom right here, this 3D figure kind of shows 3 planes. They have them numbered here and colored in different colors. We're trying to find where 3 planes intersect. Now, 3 planes might not intersect at one point. So up here in the top left, there's a lot of cases where we get no solution, where in this one, they're all parallel to each other. In this one, we have 2 planes that are parallel and one that intersects, but there's no common point between all 3. And then this one here, where every plane intersects 2 other planes, but they don't have one point in common. Now, if 3 planes intersect, like this picture down here, to form a line, that's where we're going to have infinitely many solutions, because we have all these points along this line. The most common type with 3 variables is going to look like this, where they do intersect at exactly 1 point. So our answers for this are going to be x, comma, y, comma, z, representing a 3-dimensional point. And one last thing to mention is, since we're solving a 3-dimensional plane, it's very difficult to do this graphically. So we are going to stick to our substitution and our elimination methods for solving. They still work in three variables. To save a little time and space here, I just copied this problem down. As you can see, we have a system with 3 variables, 3 equations with x, y, and z. And the first thing before we get into this problem and how to solve it is you really have to be careful. There's so many times where we make one little mistake and that throws everything off. So we're going to be very organized when we go through. So as soon as we get a problem, the first thing I want you guys to do is label each equation 1, 2, and 3. That way it's really easy to reference which one we're talking about. First, you can use elimination or substitution. Sometimes it's going to be easier to use one method, just like we've talked about with 2 variables. So for this one, it's going to show us how to use elimination. So the first thing we're going to do is we're going to pick 2 of the 3 original equations. So we could pick 1 and 2, 1 and 3, or 2 and 3. But we're going to pick one pair so that one of our variables can easily eliminate. So they ended up picking equations 1 and 2, and they noticed that our y value is the exact same. So they multiply -1 to everything in equation 1, and then they add it to equation 2 because the y variable will cancel. That's what we need. We need one variable to cancel when we pick that pair. Okay? We're going to call this new equation x plus z equals 4. We're going to call that equation 4. So we pick 2 originals, eliminate one variable, and we call that new equation 1 or equation 4. You can't solve this. So that's why you got to go back to the originals and you got to pick another pair. But when you pick that other pair, you need the same variable to cancel. So they happen to pick 2 and 3, and they notice that we need to make this first y a positive 2y. So they multiplied everything in this equation by 2. They then added the equations together, and the y's have to cancel. Since we canceled y in equation 4, we have to have a y be canceled out in equation 5. So equation 5 is 3x plus 7z equals 24. Now, from this point forward, you guys know what to do. You are going to take equation 4 and equation 5 and stack them together. You guys all know how to solve this problem because it only has 2 variables. So you can use substitution or elimination. I would look for the easier thing to eliminate, which would be x. So multiply this first equation by -3, and then add them together. We get 4z equals 12. Divide both sides by 4, and we get z equals 3. That's our first variable of 3. So now we got to take this 3 and substitute it back in. But here's the trick. You cannot plug it back into the originals. If you were to plug it into any of these spots, you would still have x and y to solve for, so it doesn't help us. So we're going to take this first value and always plug it either into equation 5 or equation 4, because we'll only have 2 variables. So they took it and plugged it into, it looks like, equation 4. So x plus 3 equals 4. Subtracted 3 from both sides and got x equals 1. Now you're going to take x equals 1 and z equals 3, and you're going to plug both of those for x and z into either of the originals. Okay, any of those work. They end up picking the first one here. It's got the smallest number, so they plugged in 1 for x, 3 for z. 1 plus 6 will give us 7. Subtract 7 from 3, and we get -4. So our answer is x, comma y, comma z. That means that these 3 planes will intersect at this one point. They again show that we're checking each of these, or this ordered pair. We are checking in all 3 originals, and they all check, so we know it's our final answer. As I mentioned at the beginning of the last problem, you can use substitution, and sometimes it does make it easier. Like in this problem, notice how the second 2 equations are missing a variable. Whenever that happens, sometimes it's easier to use substitution since you have a coefficient of 1. So we're going to take, you can take equation 2 and solve it for x. So they subtracted 5y from both sides. And then what we can do is, since both equation 1 and 3 have an x value, we can take that x equals 9 minus 5y and substitute it in for x in both of those equations. So they show that here, here's all the work, and they show it here as well. Now, look what that gives us. It gives us 2 equations here that only have a y and a z variable. Again, we're going to be able to take these 2 equations, stack them together, and use either elimination or substitution. Elimination is definitely going to be easier from this point. Multiply the first equation by 2, add them together, we get y equals 1. Take that 1, and again, you cannot, in most cases, plug it back into the originals, but notice how equation 2 only has 2 variables, so you can plug it in there. So they end up showing plugging it into y, or into equation 4. You could plug it into equation 4, equation 5, or you could plug it into equation 2 because it only has 2 variables and our y is there. So either way, we're going to get z equals 6, and then we're going to take y equals 1 and z equals 6 and plug it into one of the originals and end up getting that x is 4. So again, the ordered pair is x, comma y, comma z, 4, 1, 6. If we plug that in, it'll work in all 3 originals, and that is our final solution. Alright, so for our first step here, we always want to label our equations 1, 2, and 3. Now, I want to pick a pair of one of those 3 original equations that cancels a variable very easily. So right away, I notice equations 1 and 2. If I paired those and added the 2 equations together, they would cancel and my y's would eliminate. So I get 3x. I'm just going to rewrite them right here. And I'm going to add these 2 equations together to get 4x plus 3z equals 7. That I'm going to label as equation 4. Now, when I make my equation 5, I have to pick a different pair of original equations, and I have to make sure that my y variable eliminates because it eliminated here. So whatever variable eliminates when you make equation 4, that variable has to eliminate when you go to do your second pair. So I'm going to go ahead, and I notice that we have a negative y and a positive 2y, so I can easily eliminate that if I multiply equation 1 by... I'm going to multiply everything in there by 2. I'm going to write this down here. Equation 1, after I multiply it by 2, would be 6x minus 2y plus 2z equals 6. And now I'm going to write out equation 3, which is x plus 2y plus z equals 4. I'm going to add these two equations together to get 7x, the y's cancel, plus 3z equals 10, and I'm going to call that equation 5. Notice how equation 4 and 5 only have two variables, and they only have an x and a z variable. Now I'm going to take those two equations and I'm going to stack them together. And I'm going to eliminate another variable. And again, it doesn't matter if I eliminate x or z here, but you'll notice that the z variables or coefficients are the same. So I'm just going to multiply the first equation here. I should do a different color. First equation here by -1 to get -4x minus 3z equals -7. And I'm going to now add that together with equation 5. So 7x plus -4x gives us 3x. The z's cancel, and I get 10 plus -7, which is 3. And now I can solve for x. So I divide both sides by 3, and I get x equals 1. So that's part of my answer. Now I have to take this x equals 1, and I have to plug it back into either equation 5 or equation 4. I cannot plug it into the originals. If I were to plug it into any of the originals, I would still have a y and a z variable missing. So I'm going to take this and plug it into, it looks like maybe 4. You have some smaller numbers there. So I'm going to take that and plug it into 4. And we got that x is 1, so I'm plugging that in. Subtract 4 from both sides, and I get 3z equals 3. Divide both sides by 3, and I get z equals 1. So now x equals 1, z equals 1. Now I got to figure out what y equals. So here's where I'm going to take my x and my z variable and plug it into one of the three originals. So equation 2 was x plus y plus 2z equals 4. Plugging in a 1 for x and a 1 for y, or for z. We get 1 plus y plus 2 equals 4. Combine like terms, 3 plus y equals 4. Subtract 3 from both sides, and I get that y equals 1. So my final answer has to be written as an ordered pair, x, comma, y, comma, z. So this means that these three planes would intersect at the point 1, 1, 1.